All right, so welcome to Chapter 13. Chapter 13 is about oscillations and waves. So that would be our learning intention, would be to understand and apply properties of oscillations and waves. That's our title for Chapter 13. Specifically, this lesson 13.1, we're going to understand and apply properties of periodic motion. And so to understand what periodic motion is basically something that oscillates. So what does it mean to oscillate? Things that oscillate are things that go back and forth. For example, if you're dribbling a basketball, you dribble the ball, it hits the floor, it comes back to you, and you just keep repeating that motion. So something that repeats in a back and forth motion is an oscillation. And so things that oscillate are said to be in periodic motion. Another could be a kid on a swing going back and forth. A spring, if you stretch a spring and let go of it, it goes back and forth. That's an example of an oscillation. A pendulum would be another example of something that oscillates, and we'll look at a pendulum here in a minute. Specifically, lesson 2 is about the pendulum. So next slide, let's see what we have here. All right, it says back and forth motions are referred to as oscillations, which are things we just talked about. Oscillating systems are common and can range from a bobblehead doll to water molecules oscillating in a microwave oven. Familiar examples of oscillating systems would be a simple pendulum, like one that keeps time in a grandfather clock. So let me go show you a picture of a pendulum. So right here, this is what a simple pendulum would simply be something hanging down above the ground, not touching the ground, and then you pull it back and let go of it. So kind of like a kid on a swing. It's a pendulum motion. It goes back and forth, and that's how time is kept in a grandfather clock. Those are great big tall clocks that you've seen, is they have a pendulum that swings back and forth. And so you can see any motion that repeats itself over and over, such as the motion of a pendulum, in other words, something that's oscillating, is referred to as periodic motion. So periodic motion is motion that repeats itself over and over, like a pendulum, like dribbling a basketball. A yo-yo would be a good example of periodic motion. An echocardiogram, when you go to get your heart monitored, here's kind of a picture of it. Periodic motion has a cycle that repeats. The electrocardiogram in this figure below shows the repeating cycle, so it's showing the heartbeat every, however long that is. But that's that repeating cycle. So that would be said to have periodic motion. All right, so key characteristic of periodic motion is that of the period. The period T is the time required to complete one full cycle. And so for those of you that are in my trig class, this would be similar to the period of a trigonometric function. Once again, how long it takes something to complete a complete cycle. Only in physics, we'll refer to this with time, how many seconds it would take to complete a full cycle. So a period, we'll use the letter T for period. Time required to complete one full cycle. So it's the number of seconds per cycle. And so a period, if a period had 4 seconds, if something had a period of 4 seconds, that would mean that it takes 4 seconds to complete one cycle. For example, maybe if you had a yo-yo, and you were to throw it down with the yo-yo and let it come back to your hand, let's say that takes 4 seconds. That would be a long time probably, but if that were to take 4 seconds, then we would say its period is 4s, s for seconds. All right, also another familiar topic, or one that you see in physics a lot in this chapter, will be that of frequency and how frequency relates to the period. We just said that period was the number of seconds it took to complete one cycle. Frequency is simply the reciprocal of that. which is how many cycles there are in 1 second. So remember that period was number of cycles per second, where frequency, I just did that backwards. If you go back to that last slide, you'll see it was number of seconds. Period was seconds per cycle. Right? It's number of seconds. We talked about the yo-yo. If it took 4 seconds for it to make 1 cycle, then its period would be 4. Frequency is the reverse of that. It's the number of cycles there are in 1 second. So it's just the reciprocal. So if there's 4 seconds in 1 cycle, then that means there would be 1/4 of a cycle in a second. So go through that again. If it took 4 seconds to complete 1 cycle, for example, the yo-yo, if it took 4 seconds for it to go down to the ground and come back to your hand, that would mean that there's 1/4 of the cycle in 1 second. If it takes you 4 seconds to complete a cycle, then that means you completed 1/4 of a cycle in 1 second. So they are simply reciprocals of each other. It gives the example here of a heartbeat. The heartbeat beats about 60 times per minute or once per second. So a typical resting heart rate is around 60 for the average. Of course, that varies, but that's about 1 beat per second. So its period would be 1 second every cycle, or 1 second every beat, 1 beat every second. So in that case, the frequency and the period would actually be the same. All right, so oscillations and periodic motions. One of the key characteristics of periodic motion is its period. The period is the time required to complete 1 full cycle of motion, which we said. We talked about frequency. I think I went back a slide there. Let's move on to the next slide. Okay, here we actually have formulas to define frequency. So the frequency is 1 over the period. They are just simply reciprocals of each other. We use the letter T for period and F for frequency, and so frequency will just be 1 over T. So if the period is 4, like we talked about, 4 seconds for the yo-yo to come to the ground and come back up, if that's your period, then the frequency is 1/4. They're simply reciprocals of each other. All right, and so how do we measure these? As we had said before, period is measured in seconds, but frequency is a 1 over S typically. So if you have a period, if your period is equal to 4 seconds, your frequency is equal to 1 over 4S, meaning 1 cycle per 4 seconds. So typically for frequency, they've given this a label of its own called hertz. So anytime you have an S in the denominator, cycles per second, then that's referred to as a hertz. And so a hertz, let me just say that 1 hertz is equal to 1 cycle per 1 second. So the heartbeat is a great example of this, because the average heartbeat is around 1 beat per 1 second, and so the heartbeat has a frequency of 1 hertz. Okay, and so we would say that in this case the yo-yo has 0.25 hertz would be its frequency, because 1/4 is the same thing as 0.25. Hertz can also be in kilohertz. So kilohertz, of course, would be 10 to the 3rd power, just like it is in anything else. There's 1,000 hertz in a kilohertz and 1,000 kilohertz in a megahertz. Often you measure computer speed in kilohertz and megahertz. Not so much kilohertz anymore. When they first come out, they did, but now it's more in megahertz, which basically talks about the number of instructions per second that a computer can handle. All right, so here it's telling you once again that 1 kilohertz would be equal to 10 to the third, or 1,000 hertz. And then 1,000,000 hertz would be equivalent to a megahertz. Since period and frequency are reciprocals of one another, when one gets large, the other one gets small, which makes sense. Because just like we talked about the yo-yo having a period of maybe 4 seconds, if its period was 4 seconds, that meant its frequency was a quarter, 1/4, 1/4 of a hertz. So as this one is big, this one's small. So they are reciprocals of each other. If this one's big, this one will be small, and vice versa. All right, our next slide has some examples of different frequencies. So the hour hand on a clock has about 2.3 times 10 to the negative fifth. One cycle, it's period, so here's period compared to frequency. Period is 43,200. So that's the number of one cycle per 12 hours. So in seconds, that's about 43,200. And in frequency, that's 2.3 times 10 to the negative fifth. Minute hand, so I guess this is the number of seconds it takes it to make one cycle, or this is the number of cycles per second. So that's this number's small, this number's big. One for a minute hand on a clock, the second hand on a clock, it takes 61 cycle per minute, which is, because it goes around, the second hand goes around one time in a minute. So that's 60 seconds to complete that cycle, so its period would be 60, as frequency would be 1/60th. It would complete 1/60th of a cycle in 1 second, so that's 0.017 as a decimal. Pendulum and a grandfather clock, the human heartbeat has a frequency of 1 hertz, 1 period. So always remember when you're trying to remember what hertz means, 1 beat per second, the human heartbeat's average. Sound at lower range of human hearing, and then down here they have the sound at upper range, so sound waves is what they're referring to there. The wing beat of a housefly, so the wing beat of a housefly, it takes about a very small portion of a second for one wing beat, or you could think about 200, that housefly can beat its wings 200 times per second is basically what this is saying right here. Computer processors, 3.2 times 10 to the 9th hertz would mean the number of instructions that it can complete per second. All right, next slide is an example. And in this example, it says after walking up a flight of stairs, you take your pulse and you observe 82 heartbeats in a minute. What is the frequency of your heartbeat in hertz? And what is the period of your heartbeat in seconds? So remember, 82 heartbeats in a minute. So remember that when time is on the bottom, that's a frequency. When time is on the top, it's a period. So time on the bottom means frequency. So that's what they're giving us, 82 beats per minute. Time is on the bottom, so we know this is a frequency. So our frequency, F, 82 beats per minute. Remember, in standard international units, we would use seconds, so they're converting this to seconds. 1 minute is equal to 60 seconds. This allows us to cancel minutes. And now I've got 1.4 beats per second, and so number of cycles per second is known as hertz. And so 1.4 hertz is my frequency. So they actually gave me frequency to begin with. All I had to do was convert it into cycles per second. All right, now to find period, I simply need to take the reciprocal of frequency. So period, we use the letter T for time, and I do 1 over frequency, the reciprocal. So 1 over 1.4. If you take 1 divided by 1.4, because we typically do not leave a decimal within a fraction, and you divide these, you'll get 0.71 seconds. Remember that period is a time, and so that's given to us in seconds. All right, this slide deals with simple harmonic motion, and so it describes simple harmonic motion as periodic motion of particular importance occurs when the force pushing or pulling on an object towards equilibrium is proportional to the displacement. So that's kind of wordy, but basically it's just talking about oscillating motion where the force that's being applied is proportional to the displacement. So a spring is a great example of that. We look on our next slide here. When you take a spring, attach a mass to it, and you pull on that mass so that the spring right here, the spring is in equilibrium, okay? So force is equal to 0. No force is being applied. And up here, you have the spring being pulled back over here with this mass attached to it. And so this mass, when you let go of it, is going to apply what's called a restoring force because it's trying to restore that spring to its equilibrium state. And so you pull it here, velocity is 0 until you let go. So my initial velocity when I let go of this thing is 0, and then it starts in motion, moving in this direction. And what happens? When it gets to equilibrium, it doesn't stop. It keeps going because this force had enough force in it to push it back to this equilibrium. And what happens? Does the spring continue to just crunch up and crunch up? No. Eventually, the spring builds up enough of a restoring force in the opposite direction that it pushes it back to the other direction, and it just goes back and forth. So it's showing in slow motion kind of here what's happening. The spring's pulled back, you let go, and it returns to its equilibrium spot, and it goes past the equilibrium spot over here to this point. Now notice it says velocity is 0 again, which makes sense. It's kind of like when you throw a ball up in the air, the velocity has to be 0 in order for it to turn around and go back to the ground. Just like when you throw a ball up in the air, when you're taking the spring, its velocity is going in this direction. To turn around and go to this direction, it has to stop and then speed back up to go in the other direction. So when it gets to this point right here, where the spring has enough force to push it back the other way, the velocity for a split second there is 0 before it turns back and heads back towards its equilibrium spot. So it goes back to the equilibrium spot and eventually comes back to where the spring was initially pulled out to. So that's one complete cycle. That would represent however long it took it to do that would be its period. Notice the A down here. A is how far the string was stretched, and so the maximum amount that it gets stretched from its equilibrium is called its amplitude. So if it gets stretched 2 centimeters this way, that means your amplitude would be 2 centimeters. And notice where it landed when it went back this way, it landed back the same distance on the other side of its equilibrium. So that's what it means by simple harmonic motion. When the force is proportional to the when the force that you push with is proportional to the displacement. When that has a mathematical relationship to it, that is called simple harmonic motion. All right, and so this spring can continue to do this multiple times. This is just one cycle of this spring doing this. All right, so as is in the figure, the cart is displaced to x equal a, and then released from rest. So basically everything they're saying on this slide, actually the next couple of slides, is basically what I just told you about that spring. And so here it's saying that the motion of the cart can be divided into 4 parts, each part taking an equal amount of time, and so 1/4 of the period. So remember, period is always referred to as the letter T. So each particular part of that motion would be 1/4. So if I go back and look at that spring, and from here to here, so the spring starts here, moves to here, then to here, then back to here, and then back to its original spot. That's what this whole picture is showing you. So from here to here, that's its first segment, to here, back to here, and here. So you can think about dividing it up into 4 equal distances, then each part of that move would be 1/4 of the period. All right, so it says, suppose you attach a pen to the cart in the previous figure and let it trace the cart's motion on a strip of paper moving with constant speed. The strip of paper or chart would record the cart's motion as a function of time. Such a recording is shown in the figure below. Notice that the motion looks like a sine or cosine. This should say sine, not cos. That little c should not be there. So if you've been in trigonometry and you know what a sine or cosine curve looks like, then this will look somewhat familiar to you. And they kind of have it in this picture. I'm going to show you a better picture of this thing right here so you can see what's going on. Here it is right here. So here's our spring that we had before. And here's its equilibrium point right here at 0. And so they're going to take this thing, pull it back, and let go of it. And as it starts to move, they've got this roll of paper down here, and there's a pin that's hooked to this weight. And so this paper is going to move at a constant rate while the spring is bouncing back and forth with the pin attached to it. And I guess the pin's right here. The pin will trace its motion out on this piece of paper. This piece of paper is going to roll by with this thing going back and forth, and so as the paper's rolling while this is going back and forth, this pin is going to make this motion. And so if you take this motion and you turn it on its side, it looks like what we would call in math as a sine or a cosine curve. It mimics that, which is this picture right here. And so the amplitude is the distance from here to here. That's how far the maximum amount the string was stretched, and then the maximum amount that it bounced back over here. And so you can see this motion right here. One complete cycle would be from here to here. That's one complete cycle. And whatever time it takes to do that would be your period. So in this slide, they talk about the difference between a soft spring and a stiff spring. Remember that in Hooke's law, you use the formula force equals K times X, and K was the spring constant. So when this number was big, that meant you had a stiff spring, and when the number's small, that means you have a soft spring. So if you have a soft spring and you hook a mass onto it, then it will oscillate slowly as compared to a stiff spring. If you hook a mass to a stiff spring, it's going to oscillate more rapidly. So if you have a soft spring oscillating slowly, that means the period is going to be larger because it's going to take longer to complete a cycle. So when this number is small, our period will be large. So they're inversely related. And if you have a stiff spring, that means you have a large K value, which will result in a smaller period. So once again, as K gets big, the period will become smaller. And also, if you the amount of mass you attach to the spring also makes a difference. If you attach a large amount of mass, then that will also slow down the oscillations and increase the period. And so all of this is going to tie into our formula. And so here's what you really need to know to work problems is the formula for period. Period can be calculated by taking 2 times pi, and then taking the square root of the mass that you hook onto the spring divided by the spring constant. So this is a formula to calculate period if you have a mass on a spring. So a mass attached to a spring. To calculate period, you take the square root of the mass over the spring constant and multiply it times 2 pi. And for the letter, for period, we use the letter T. Now, of course, frequency is simply the reciprocal of that. So if I wanted a formula for frequency would equal 1 over 2 pi times the square root of K over M. You just flip everything over. I'm kind of surprised I didn't put that formula on the sheet. But period is this, and frequency is the reciprocal to it. You just flip it over. And so think about if you were to increase mass is in the numerator. So when you increase the numerator, that will increase this number. So as mass goes up, period will go up. But notice K is in the denominator, so when something's in the denominator and gets bigger, that has an inverse relationship to this. So if this number gets bigger, that will make this number get smaller because they're inversely related. And over here, as K gets bigger, frequency will get bigger. And as M gets bigger, frequency would get smaller. Also, don't confuse. In fact, I shouldn't probably be using a capital F here. I think they use a lowercase f for frequency, and the reason for that probably is we use capital F for force. So remember, this is Hooke's law that we used to figure out how far a string was stretched if we knew the constant and the force. But this F stands for frequency. And notice neither one of these formulas have an X in them. Notice neither one of them use amplitude either. Amplitude has nothing to do with determining the period or the frequency. It's just the mass and the spring constant. So amplitude will not affect period. All right, so here's an example. It says you have a 20.22 kilogram air track cart and it's attached to a spring with a spring constant of 12. What is the period? So they're asking you to find period. You know that we just went over the formula. It was 2 pi times the square root of m over k. And they told us m and they told us k. They told us that the mass was 0.22 kilograms and the spring constant was 12. So if I simply divide those numbers and then square root them, multiply by 2 pi, I'll get a period of 0.85 seconds. Just plug the numbers in and get it typed into the calculator correctly, and you've got it. All right, astronauts floating weightlessly above the Earth can't just jump on the bathroom scale to determine their mass. However, the mass of an astronaut can be measured using a body mass measurement device, the BMMD. This device is essentially a chair attached to a spring having a known spring constant K. The mass of the astronaut in the figure below is being determined by measuring that. So we'll look at that picture. Here's a picture of that chair. This chair is somehow hooked to a spring, and they know the spring constant. And then that spring, they can figure out the period on that spring. That can be measured based on whoever sits in it, and then they can plug it into that formula and solve it for M. So that's one way of calculating mass in outer space. All right, and this is our last slide for this lesson. Suppose you have two identical mass spring systems. Suppose you give one mass twice the amplitude of the other. What effect does this have on the period? Well, if you remember, the formula doesn't have amplitude in it anywhere, so amplitude is not going to affect period at all. And that's what they're saying here. Amplitude has no effect on period. The larger amplitude causes a larger force to be exerted by the spring, and this larger force in turn causes the mass to move more rapidly. So the speed of the mass increases just enough to make it cover the same ground. So in other words, if you were to take the spring and pull it back farther, what they're saying is you'll just have more force and it will catch up, and it'll take the exact same amount of time to go from one place to the other. So if we go back and look at that picture of the spring right here, what they're saying is if you take this and you pull it back farther, will it take more time? And surprisingly, it doesn't, because when it's pulled back here, it's got more force. So when you let go, it travels more rapidly and actually will catch up, and the period will end up being the same time. And so what I mean by it takes it the same amount of time to get to its equilibrium point. Okay? Doesn't necessarily mean that if you pull here, the time it takes to go here to here, but the time it takes you to get to the equilibrium point would be exactly the same. And that was our last slide and all we have for 13.1. There will be an examples video and your problems will be posted in Schoology.